Hello everyone. Today we will continue to our lectures. I don't say not a lecture. And I did some summary for the previous videos we recorded and investigated, which was about the inflation, actually the expansion of the universe. So we discussed the Hubble constants, and we wrote down the equations of Hubble and expansion respectively to the time, which is a process that is required to observe any physical event, and write down the equations because the time is a variable, and the presence of any variable is the essential reason that we are writing down the differential equations, and we are just solving them. And it is also evidence, or the validate, honestly, it validates that the expansion is dependent to the material and the chosen era of the universe. So we will, honestly, in this video, we will discuss the dynamics. So we will discuss them. Yeah. So let me read some summary about the previous videos and what we reached after many assessments we did. What we inferred is actually what I'm reading right now. So the universe looks completely uniform in all directions, which means that it is homogeneous and isotropic for all observers, and which means that the flat case is interrupted right now. Most of the elements in the universe did not form at the Big Bang, but formed actually they formed afterwards, laterly, I mean. At the presence of the stars and the galaxies, the material distribution of mass is growing up, because they are the essential reasons why they are forming. I mean, why the elements and the other isotopes are forming, and as the universe expands, the material stretches out and so on, that it separates, I mean, the distance between them and the interactions between them is going to be interchangeable. So that is the essential reason why the material is still being formed and so on, still forming, and it was. And actually, at the earlier times, that there are two elements that formed primarily, and they are hydrogen and helium, and primarily formed in the Big Bang. In general relativity, we will add, and also you can predict, gravitational repulsion is created by the negative pressure. So the positive pressure and the negative pressure takes place right now, and it is important. For any ordinary matter, the pressure is positive, okay? But for the repulsive gravity, the pressure is negative, which is the essential reason that the universe accelerates so fast, and the velocity or the ratio of this expansion is growing up because of the repulsive gravity that created by the dark energy and the dark matter. These are the essential reasons of repulsive gravity. But we can predict also, for example, we may expect that because of the gravitational attractions, the objects or the materials inside of the universe should become closer. I mean, they should be pulled up, honestly, towards the center of the mass. So the distance between the objects must be decreased as time elapses. But this is actually happening in the presence of positive pressure, which is the gravitational fields. At the presence of negative pressure, the expansion is just increasing because they push together, not pull but push. So this is the essential reason why the universe expands so fast, and still it is. So let me read more about this. So the combination of general relativity and modern particle physics theories predict that at very high energies, the gravitational repulsion can be created. So also caused, by the way. Energy densities can produce gravitational repulsions, unlike Newtonian physics, where it's only mass densities that produce gravitational fields, what I'm saying right now. So these are just a summary of the previous videos of cosmology that we recorded together. So you may recollect that we assume that the galaxy of ours are just a single dot in the whole universe, and we observe nearby galaxies, right? So as to write down the equations that is suitable to explain the expansion of the other galaxies. Actually, the dynamics of them, right? In the given conditions, and actually the conditions are high and strong, I mean, so enormous value of gravitational forces and attractions each other. So also in this video we will discuss the sphere that includes a mass density inside of it, and so on. We will write down the equations of the potential energy of gravitation and then turn back into the force and just Newtonian equations for expansion. These are just the essentials of this video. The gravitational repulsion created by this small patch of repulsive gravity material undergo exponential explosion. So, which means that in the presence of gravitational repulsion, the expansion or the rate of it is exponential function. So fast. So larger amounts of inflation are perfectly consistent with what we see right now. And actually, for ordinary gravitational fields, we have a negative energy, right? We will write down in this video afterwards. So here is an important fact. So I intend to write down. Actually, here is time contraction and time dilation. We will turn back into the redshifts and the cosmological redshifts, by the way. It is not the same as the redshifts we observe from stars. Not something same. So, yeah. We'll write down the equations right now. Actually, this is what we observe, and yeah. The patch expanded exponentially by a factor of at least 10 to the 28. But it could expand much more. And by the way, it could be, it could expand much more of this value. So inflation lasted, it's over, maybe 10 to the minus 35 seconds after the Big Bang. So the region destined to become to the presently observed universe was about the size of a marble. So this is something so important. This is just seconds, okay? And this is just a ratio, okay? The expansion of the ratio. The repulsive gravity material is unstable. So it decayed like radioactive substance, ending inflation. The decay released energy which produced ordinary particles, forming a hot, dense, primordial soap, and what we talked before, and so on. The density of the repulsive gravity material was not lowered as it expanded. Although more and more mass energy appeared as the repulsive gravity expanded, total energy was conserved. So, which we can also easily predict that the total charge of the universe is also conserved. It's always same, never changes. So it is as the material density of the universe. So we will call in this video afterwards, the omega is equals, and also it stands for the ratio of the density. The critical density, it could be is actual mass density divided by the critical mass density. Okay, so it can be bigger than 0, and actually the first is that the critical case where it can be equal 1, bigger than 1, and smaller than 1. For today's universe, we know that the mass density of the universe is nearly flat, which means equals to the 1. And actually the value of it is, let me write down, percentage, by the way. So as you can see, so close to the 1 is a and constant number, by the way. So omega, which and actually when the value of it is bigger than 1, it means that the closed geometry of the universe, closed universe, we will, and this one is actually the open universe, we will call it. The flat universe means Euclidean, and as opposed to the non-Euclidean curved spaces that are also allowed by Einstein's general relativity. If omega in the early universe was slightly below 1, it would rapidly fall to the 0, because you know that the expansion. So why the density should decrease and goes through the 0? This is the essential reason the question actually. The reason of it is because, for example, number of atoms or light beams per unit surface or any given space like volume will be decreased as it expands, because the volume or the size of the marble or the patch we choose is growing up. The radius or the surface is increasing. So for the unit area, which is infinitesimal, and the number of given particles or just radiation that emitted by the surface will be decreased. So the density is decreasing. This is just what we infer from this equation. If omega was slightly greater than 1, it would rapidly raise to infinity, what we call open and infinite universe. And the universe would recollapse and no galaxies would form. And the other case, even today, the universe should have a critical density, at least, by the way. The latest observations of us by a Planck satellite, omega measured, as you can see, near to the 1, not greater, nor, neither greater than it or nor smaller than it, lower than it. So also today's universe, also including the dark energy, also known as the vacuum energy, is also known as cosmological constant. The quantum vacuum is far from empty, so a non-zero energy density is not a problem. In quantum field theory, the energy densities of quantum fluctuations diverge. So all wavelengths contribute, and there's no shortest wavelength. This is just a consequence from the quantum field theory. But in this video, we will not go deeply by the quantum theories and so on, what we call. Okay.